Hey guys, welcome to lecture number 13 in Calculus 1. Well, now in this lecture we will see some applications, real world applications, especially in physics of derivatives, especially of the notions that we learn in lectures 11 and 12. Well, I will dwell more on rates of change. We will talk about the modeling of rectilinear motion, or we will talk about the relative rate of change, and also we will basically introduce I will introduce you to the world of mathematical modeling a bit, and you will see why the derivatives are very important here. All right, let's get started. So let me start with rates of change, but we'll talk about the modeling rectilinear motion, as you can see in the title. And so let's write it, rates of change. And we will talk about modeling rectilinear motion. Okay. And I would like to start by, I would like to start by drawing a picture. So recall from previous lectures, right? We talked about rates of change. So recall from I don't know, from this chapter section, I think it was the first section, from the first section of chapter 3. Let's recall the following picture, and I will draw the XY axis, as you can see here. So here I have the point x naught, right? And here I'll have the point x naught plus that difference delta x. Here I'll have f of x naught, and here I will have, let's say, f of x plus delta x, right? Okay. Now this guy here, so this will be the point x naught and f of x naught. Let's put it here. And here it will be this one here. Okay. Now we would like to see, well, the difference between these two, right? Let me just draw the line between these 2 points. And the line keeps going. Okay. And now the difference here will be delta y. Let's call it this way. And the difference here will be delta x. All right. So the rate of change, let me write it here. The rate of change is equal to delta y over delta x. All right. So that's for a linear function. Let me put it. Okay. So that's the rate of change. So we know this. Okay. Now for a linear function, so keep in mind that for a linear function, the rate of change is a constant. So let's write this. Rate of change is a constant. Right? So basically we can say that, let me put it here, that the slope between 2 points is the same everywhere on the graph. Everywhere on the graph. Okay, so we have to keep this in mind, right? And now let's see, so this is when we deal with a linear function, but let's see, so let me point out, so this is what happens when we deal with a linear function, but we would like to see what happens when we deal with a non-linear function. So let me draw the same graph, and you will see what happens here. So let me draw, the picture will be a little bit more complicated. Okay, okay, on the XY axis. And now let's say I'll have here a point x0. Here I'll have another point x1. Here I have, let's say, x0 plus delta x plus the difference. And here I'll have, let's say, x1 plus delta x. All right. And now the same thing will happen. Let's say I will have here f of x1. And here I'll have f of x0. So the points, let's say, here I'll have a point. Let's just say P. Here I'll have let's say another one. At the intersection, let's say R, right? Just because this will be like a curve anyway, we'll see that. And let's just say here I'll have another point, let's say f of x0 plus delta x0. And here I'll have f of x1 plus delta x1. So f of x0 and this guy will meet here at this point. And these guys let's just say, so it will be something like this. Well, I didn't plan to make this look very linear, but anyway, so it will look something like this. Let's just say that this is the curve. Okay. I think you can see it. It's pretty clear, I hope, the picture. All right. And now, so here I'll have the point, let's say Q, and this will be the point S, right? P, R, Q, S, whatever. Okay, and now let me, so the difference between these, so let me change the color a bit so that you can see it better. So the difference between x0 and this guy from here to here is delta x, right? Oh, sorry, here I forgot to put x0. So here it's x0, sorry about that. So this will be delta x0, right? Okay, and now from x1 to x1 to x1 plus delta x. So this guy will be, oh, sorry, here will be delta x1. I always forget this. So this would be guy will be delta x1. Okay, right? Okay, and now let's see here. Let me change the color a bit. So here, between R and Q, let's just say that here from here will be delta y0, right? And from here to here, this will be delta y1. Right, as you can see, the differences between on the or horizontal and on vertical. And now let's just interpret this picture a bit. So we can write, well, in this case, we can write that we deal with a nonlinear function. So let's write this. So we have a nonlinear function. And here, So in this case, let's see, what do we have? The rate of change. So if you look at the picture, I would like to see what is the rate of change between P and Q. So let me draw this line. What color should I use? Okay, let me use this. So from P to Q. So let me draw this line, right? From P to Q. Okay. And now, the same thing I will do for this one here. In fact, let me draw this line again from R to S. So from here all the way to here. So let me draw this line as well, right? So again, ooch, this is a line. So I have these two lines, right, in blue. And now, and this light blue. And now let's interpret this. So let's see, what is the rate of change right, between points P and Q. So the rate of change between P and Q is given by, so let's look at the picture, P and Q. So it will be dy0 over dx0. So this is dy0 over dx0, right? So this will be nothing else. So let's write it. So this will be the slope of the second line PQ. Of the second line, secant line PQ. All right, so this is the slope of the secant line PQ, so keep that in mind. And now, the same story if we want to see the rate of change between, well, if we look at the picture, if we want to see the rate of change between R and S, we have, this would be clearly, if we look at the difference, as you can see in the picture, is delta y1 over delta x1, right? So look at the points where they are. So between R and S, if you look at the picture, it's quite clear, okay? So this would be delta y1 over delta x1. So if you look at this guy here, right? So this guy here is nothing else than just the slope of the secant line RS. So this is the slope of the secant line RS. All right, that's beautiful. And now let's see, the main idea is that, well, we want to see what happens for a nonlinear function. So we have seen what happens when we deal with a linear function. So for a nonlinear function, the rate of change is variable. Is not constant this time, is variable. And that's the word we should keep in mind, is variable. Right? So basically, let's put here, it depends on the points chosen. So that's why we have chosen 2 points there so that you can see it better, right? As you can see here, I have 4 points on this graph, so you can pick any 2 points you want. But anyway, we pick these 2 by 2 points because their distance between them is delta x1 on the x-axis or delta x0, and on the y-axis is delta y0 or delta y1. But anyway, I think you get the picture. It's quite obvious. But now let's see what happens in general. So in general, So in general, we have the following. Suppose that y is a function of x. Let's say y equals f of x, right? And now we consider a change from x to x plus delta x. Okay, then the variable y changes from f of x to f of x plus delta x, right? Obviously. And now we can say that the average rate of change is equal to, we can say that it's the change in y over the change in x, which is nothing else if we want to look at the formula. So the change in y will be f of x plus delta x minus f of x, right? And the change in x will be nothing else, it's x plus delta x minus x, which is nothing else than delta x. So let's keep this in mind. So this is what we call the average change, average rate of change. So it's given by this formula, right? Okay, now we would like to see what do we mean by the instantaneous rate of change. We would like to talk about this. Rate of change, okay. So let's see what happens in this case with the instantaneous rate of change. Well, let's see. So we suppose that, suppose that f of x, we have a function of variable x is differentiable at the point x equals x naught. Then the instantaneous rate of change, right? The instantaneous rate of change of y of the function y equals f of x, right? With respect to x, right? At the point x naught is the value of the derivative. In fact, let me write this with red. So is the value of the derivative right of f at x naught, right? So that's what we need to know. And basically this will be nothing else than just, let's write it, instantaneous rate of change this would be equal to the derivative of f at x naught. Or we can write this, if you want, in Leibniz notation. So sometimes we will prefer this notation, is dy over dx. So is the derivative of y with respect to x, and now we'll write this at the point x equals x naught. So that's what we need to know. So that's the instantaneous rate of change. Okay, now let's draw a picture so that you can see it better. Let's draw this. So we will, let's draw a curve like this, right? And let's just say here we have a point P, and here will be, we'll draw, okay, so it'll be tangent here at P. Okay, and here will be the point, let's say x naught. Well, as you can see, this is nothing else the slope of the tangent line, right? This is what the derivative actually is. So let's write this. So instantaneous rate of change. So the instantaneous rate of change right at x naught will be nothing else is this guy here, like we said, is dy over dx at the point x naught. So that's what it is. And this is nothing else, is equal to the slope of the tangent line to the curve at x equals x naught. And now, well, I think you got the picture now. As you can see, the slope of the tangent line. So it's tangent at this point. And now let's see an example. So let's illustrate this through an example so that you can see it better. In fact, please look at the picture again, right? We have this curve, and this is the slope of the tangent at that point, right? Okay, that line is tangent to the curve at the point P. And now let's see an example. All right, and now let me give you a nice example of real, in fact, it's a nice application of, well, this can be like a real world situation. And let me just say, suppose that John travels, let's say, from Lubbock to Dallas. Well, you know, it's a pretty long drive, if you ask me. Well, before I moved to Lubbock, I didn't know that it was like 5 hours and almost 6 hours away from everything, like Dallas, like Albuquerque, well, Oklahoma City, whatever. So basically, it's in the middle of nowhere. So let's just draw this, the distance between Lubbock and Dallas. So let's just, in fact, let me draw it here. We have John, who's traveling from Lubbock to Dallas, right? And let's just say that the traveling is like, here we'll have the time, which will be in terms of t, a function of t. And here we'll have the displacement, which is a function of d, right? Oops. Right. Okay. And let's just say that, well, the distance between Lubbock and Dallas, as far as I'm concerned, I think it was like Lubbock to, let me write it here. I think it was something like 346.6 miles. Okay, let's put it somewhere here. 346.6 miles. All right. And the time, well, it says, well, if, it's 7 hours. Right, so that's the, in fact, this is the time, so it's 7 hours time of t. All right, and now let's see how John travels. So it starts from 0, so it will go like this, and then like this, and then like this, and then like this, and then like this. So it will reach to destinations, right? So it starts from 0 here. Okay. Now let's see, at the point, let's say here S. So this will be, let's say here, 122 miles. And now let me put something in here. For example, let's point the point A. Well, this is, let's say this S comes from Sweetwater. So let's say here it has like 1 hour and 47 minutes. So this is S from Sweetwater. And let's just say, so A comes from Abilene. So this would be at 2 hours and 22 minutes. So A is Abilene. And eventually it will reach to Dallas, right? As you can see, it's right here. This point D, let's say. Okay. So as you can see, this is the distance, right? The way that John travels from Lubbock to Dallas. All right, and now, well, we would like to, as you can see, let me draw the line between these. Of course, the shortest distance between Sweetwater and Abilene is a line, is not like going like this. But anyway, the question is, because this is like a real situation, we would like to see what is the average speed. So the question, let's say, that we want to ask is, what is the average speed between Sweetwater and Abilene? So we would like to see that. Well, the average velocity, so the average speed between these, well, we know that the average velocity is nothing else than the displacement over time taken. Okay, and now let's see, the displacement is, you look at the displacement between the two. So this would be what? So let's just say the Abilene, oh my God, I forgot to say here something because okay, let's just say here Abilene is at 130 or 163 miles. Because I forgot to put the displacement, right? All right, so this would be what? 163 minus 122 over 2 hours 22 minus 1 hour 47 minutes. So this would be, if you do the math here, so this will be 41 over how many minutes? 2 hours. So this is less than 2 hours a bit, so less than 1 hour, sorry. So it's 0.58. So it's 58 minutes. So 0.41 0.58 hours. So this will be 41 over 0.58 hours. So this would be something like around 70.7 miles per hour. So this is how we find out the average velocity between two cities, in our case, Whitewater and Abilene. Right? So this is the average velocity. This is nothing else than the average rate of change. So let's write this here. So this is the average rate of change. Right? Okay. But now what if I ask you another question? So there's the first question. Now let's see the second question. So I asked about the average velocity, but what if I ask you about the instantaneous speed at Abilene, for example? So what is the instantaneous speed at Abilene? Well, so we want to see this. So this is nothing else than instantaneous speed. So is nothing else than the slope of the tangent line to the graph at the point A, where Abilene is. So this is nothing else than the slope. In fact, let's rewrite this in a different color. The slope of the tangent line to the graph at A. So right, when I say A, I mean Abilene. So the slope of the tangent line, so let's draw the tangent line here at A. Let me use a different color. Maybe I should use green. Okay. So the slope of the tangent line. So let's. So this would be something like this. Right. So this is the. So this is the tangent line at A. Okay. So guess what? This will be nothing else. If you want to look like this, okay, let's write it again. Is dy over dx at the point, guess what? What point? At x equals x naught. At the time where I reach Abilene. So what is the time? So this would be nothing else than just, where in our case, x naught will be, let's look at the graph. Let's see at where do we have Abilene? Look here. At x naught will be 2 hours and 22 minutes. So 2 hours and 22 minutes. Right? So you can see this is nothing else than just the derivative. So here, let me point out a remark. Note that if we know the mathematical formula, because we don't know how what is exactly the graph is, what is the function? What is that? The graph of what function is that? But if we know the mathematical formula, right, for the function between the time and the distance, right? Then we will be able to find the related derivative. So we can do this. All right. So unfortunately, when you look at this, we don't know how this, what function is this, but if we know at least on one portion how the function looks like, then yes, we can actually find all this. But usually in problems, when you will have this related rates type of problem, it's when we have a movement between something, let's say two cities, is actually described by a function. I will tell you exactly, is described by this function. All right, beautiful. Now let's do some exercises. So let's say exercise 1. Because I would like you to see how we apply this to a certain function. So now let's see some concrete functions. So now, for example, I'm interested in find the, let's say, the rate of change. Well, this is easy. Or maybe let me find at what rate the function, let's just say y equals x squared sine of x. So as you can see, this is a concrete function, is changing with respect to x when x equals pi. So we're interested in this, right? Okay. So let's see. So when you see what rate, clearly, as you can see, we have the keywords here, rate and change, rate of change. So in other words, we would like to see the instantaneous rate of change. So for any x, the instantaneous rate of change is given by, so this will be nothing else than just the derivative dy over dx, which is the derivative of this function, x squared times sine of x, everything over dx, right? And now let's compute the derivative. Basically, we have to compute the derivative of y of x, which is nothing else than just the product between x squared and sine of x. So we apply the product rule here. So let's say that. So by applying the product rule, we have the following. We have that this is sine of x times dx squared over dx. So we'll take the derivative of x squared first, plus x squared times d sine of x with respect to x. And this will be equal to, so let's write it here. So this would be nothing else than just sine of x times 2x plus x squared times cosine of x. And this would be, let's write it in this way, 2x sine of x plus x squared cosine of x. Okay, so that's the instantaneous rate of change. So basically it's just the derivative. But now look at, so that's the instantaneous rate of change. But now we look at what point we're interested in. So this would be the rate when x equals pi is given by the following. So basically we will have to compute the derivative of y with respect to x at the point x equals y. So this would be nothing else. We're just going to replace this guy here. So this would be 2 pi sine of pi plus pi squared cosine of pi, which is nothing else. Well, sine of pi is 0, cosine of pi is -1. So this would be 2 pi times 0 plus pi squared times -1. So this would be equal to a negative pi squared, right? And that's it. That's the end of the problem. As you can see, it's pretty straightforward. So when you are asked about what range a function is changing with respect to x, when x equals some number, then you will think about the instantaneous rate of change. All right. So that was exercise 1. Now let me think of another one before we talk about the relative rate of change. Let me do another exercise 2. And for this exercise, let me consider the following function. Let me take a quadratic function. So let me take f of x is, so it's x squared minus 4x plus 7, right? So this is my function. And now we're interested in 2 things. So the first thing is to find the average rate of change. Find the average rate of change of f, of my function f, with respect to x, let's say between 3 and 5. With respect to x. Right? Between x equals 3 and x equals 5. Okay, that's the first thing. The second one is find the instantaneous rate of change. Instantaneous rate of change of f at x equals 3. Right? So let's look for the keywords here. Look at the first one. So it's about the average rate of change. And here is the instantaneous rate of change. Well, it's quite clear what to do when you look at it, right? So what you should do here, it's basically just you apply the 2 formulas, right? You look at this. You see we look at these 2 formulas here for the average rate of change. So it's quite clear what to do. So basically you would look at the change in x, then the change in y. Basically you look for delta x, delta y. And for the second one, in the case of the instantaneous rate of change, you look for the derivative basically of the first derivative of the function evaluated at the point x equals 3, right? So this is what you have to do. All right, look at it. And now let's get to work let's apply these 2 functions, these 2 formulas, sorry. All right, let's do it. So the first one, so the change in x is equal to, is delta x, which is nothing else than, well, you see, I'm interested at these 2 points, x equals 3 and x equals 5. So this would be 5 minus 3. And the change in y, well, is what is delta y, and this will be nothing else than f, the function f evaluated at 5 minus the function f evaluated at 3. Basically, it's just the difference between f evaluated at those 2 values, right? Well, it's quite clear now what to do. Let's evaluate this. So this will be 2 here, and now f of the 5 minus f of, so f of 5, if we look at our function, so this would be 5 squared minus 4 times 5 plus 7, and this would be nothing else than just 12, and f of 3 will be 3 squared minus 4 times 3 plus 7, which will be nothing else than 8. And now we can, the average rate of change, so the average rate of change is nothing else than just is equal to f of 5 minus f of 3 over 5 minus 3. So this would be equal to so wait, I made a mistake here. This is not 8, this is 4. Yeah, this is algebra. Anyway, so this would be 12 minus 4 over 5 minus 3. Well, if you want to look, this is 8 over 2, which is 4. So that's the average rate of change. But now for the second part, basically, we know that, so we have that the derivative of f prime of x, is nothing else, so it's the derivative with respect to x of our function, which is x squared minus 4x plus 7, which will be, well, if you differentiate here, this will be nothing else than 2x minus 4, right? And now the instantaneous rate of change right, at x equals 3 is nothing else than dy over dx. So the derivative evaluated at this point, x equals 3. So this would be nothing else than just 2x minus 4 evaluated at x equals 3. And now you can plug in, and this will give you 2. Anyway, so it's just the derivative evaluated at 3, so it wasn't a big deal. All right. All right, I think you got the idea how about the average rate of change, about the instantaneous rate of change. Now I would like to veer towards something else as well. I'd like to talk about the relative rate of change. That's important. So relative, you'll see that this is related to the instantaneous rate of change, but it's not the same. So relative rate of change. Okay, so the relative rate of change of y equals f of x, right, at the point x equals x naught, is given by, so let's write it. Okay, I'm going to write it with red again. So relative rate of change. So this would be equal to, if you look at it, so this is f prime of evaluated at x naught over f of x naught. So that's the formula. Look at it. And now let's see how are we going to apply this formula. Let's see an example, a quick example, because this will be important. For example, let's see the aerobic rate. So let's define the aerobic rate is the rate of a person's oxygen consumption right, and is sometimes modeled by the function A defined by, so this function is A of x is the same as 110 times ln of x minus 2 over x. So let's just say that is modeled by this function, where this x is nothing else than just the person's age. Okay, and we're asked the following question. So question, what is the relative rate of change? As you can see, the magic word here, relative rate of change, right? As you can see above, we talked about this. So what is the relative rate of change of the aerobic rating of a, let's say, 20-year-old person and part B, 50-year-old person. All right, I want you to look at the problem. And as you can see, basically, we have to compute the derivative of that function, and then we have to evaluate it. Probably, you guess, when x equals, well, we have to compute first the derivative, then we have to use the formula for the relative rate of change, and then guess what? We have to evaluate it at x not equals 20 and x not equals 50. So that's the main idea of the problem. So let's see. Solution. So let's see. So now let's compute the derivative. First, we compute the derivative right of a of x. So let's compute the derivative of this function. So we have that a prime of x is nothing else than just 110 times, let me write it like this. So it's ln of x minus 2, everything over x, and everything prime. So this guy will be nothing else than just 110, and then we have to compute the derivative with respect to x. So d over dx of ln of x minus 2, everything over x. So we have to compute the derivative of this guy. And guess what? We will apply the quotient rule. So by applying, and I'll write here the quotient rule. So by applying the quotient rule, this would be equal to, let's see, so 110 everything over x squared times, and here I'll have the x times the derivative with respect to x of ln of x minus 2 minus ln of x minus 2 times the derivative of x with respect to x. So, well, and this would be equal to, if you, anyway, I'm just going to write it directly. So that would be 1 over x times 2, x will be 1. 1 minus 1. So this would be, okay, 110 over x squared times, so I'm just going ahead with the algebra, but I'm sure you can do it. So this will be nothing else than just 3 minus ln of x, right? So that's the derivative of the function. And now we're not done yet. We're not done because look what we're asked to do. We're asked about the relative rate of change. Keep in mind, the relative rate of change is not the derivative, it's the derivative over the function. So we have that the relative rate of change is the derivative f prime of x naught over f of x naught. And now we have to evaluate this. Well, we can write this. So this would be 110 over x naught squared times 3 minus ln of x naught. Everything over f of x naught, which is, what is it? 110 over x naught times ln of x naught minus 2 over x naught. Okay, and now clearly we can do some algebra here. So this would be equal to, if we do some algebra, x naught will be, so it will be nothing else than just 3 minus ln of x naught over did I forget something? Let me see. So that would be x. Three minus x naught. No, sorry, I put an extra. Okay, a mistake here. So this is just ln of x naught minus 2. All right, now we're good. So this would be 3 minus ln of x naught, right, over x naught times ln of x naught minus 2. Okay, so this is the relative rate of change. And now let's see, right? So this is the relative rate of change. Look at it here. And now the only thing we need to do is just to see what happens for a 40-year, for a 20-year-old person. So for a 20-year-old person, this x naught is 20. We have that the relative rate of change right is nothing else than 3 minus ln of 20. So we just replace x naught by 20 over 20 times ln of 20 minus 2. And this would give me, well, approximately, this would be, let's see, let me see. Anyway, so this would be 0.001 whatever. 001, 00, let me, 002. 21, whatever, anyway. And now the second one for a 50-year-old person. So in this case, we'll take x naught to be 50. We have that the relative rate of change will be nothing else than just 3 minus ln of 50 over 50 times ln of 50 minus 2. And this would be equal to, we'll give negative, so this would be 0, negative 0, 0, what is it? Almost 1, huh? 0, 0, 0, no, almost 1, yeah, something like, let me see. Yeah, 95, okay, whatever. Anyway, So this is how you deal with this problem. When you ask about the relative rate of change, you always think of the derivative. So when you think of relative rate of change, you always think of this guy, f prime of evaluated x naught over f of x naught. So that's the relative rate of change. Okay, now let's talk a bit about the introduction to mathematical modeling. And let's see what this is all about. This is a very nice introduction. To mathematical modeling. And let's see what this is all about. So let me draw the following picture. So let's see, suppose we have a real world problem. And we have plenty of them. Well, as you can see, these days we're actually battling this pandemic with the COVID-19, and everybody's trying to come up. In fact, some of them they actually did. They came up with some mathematical models to model the spread of the virus of the COVID-19, for example. That's pretty interesting. And in fact, I saw some of the models. They involve like differential equations. Well, differential equations involve derivatives, basically what we learned here. So there is a real world situation where you can use, we can use all this stuff. So we have the real world problem. And now we, we would like to abstract, how should I say it? Abstraction. So we would like to see what is the abstract version of this real world problem. So basically we'll turn this into a mathematical model. Right? And then from here, we will see, we would like to make some predictions. And now, when we come up with this mathematical model and we make some predictions, we want to go back to the real world. We want to see how those predictions actually fit into the real world picture. So we go back to the real world problem and we compare the results. We compare and interpret. So that's what we do. But we need to come up with the mathematical model, and we want to see if this model is actually good. All right. One of the models that I would like to talk about is, well, there are some of them, but I would like to talk about motion. Well, you see motions in everyday's life. Motions of, I don't know, we move, for example, as people. We go from places, well, not as much these days, but we move a lot. So, and this motion is different, they're of different types. For example, it can be rectilinear motion, right? It can be circular motion, it can be periodic motion, right? So we can have this. So let's talk about motions. And the first one I have in mind, so that's rectilinear motion. So what happens in the case of a rectilinear motion? Well, as you could guess, the objects move along a straight line. So they move along a straight line. So this is what we call a rectilinear motion. So everything that moves is just a straight line. It doesn't go like this or whatever. It's just a straight line. Okay. So for example, let's see some examples. The motion of a vehicle on a straight road. So the motion of a vehicle on a straight road. Well, usually you're supposed to go straight on this road. When you have a straight road, you don't go like this. Well, that's you're supposed not to. So if you drive normally, so you're going on a straight line, right? Let's see what else we have here. So that was the first one. Maybe the second one. For example, up and down motion of a yo-yo. Motion of a yo-yo. Right? What else? For example, the motion of a rocket on its early in its flight, right? So early in its flight it goes straight, and then at some point it will curve. So the motion of a rocket early in its flight. Okay. So these are 3 examples, and I'm sure you can come up with other examples as well of rectilinear motions. And now let's see some other. So let's talk about circular motion. And let's see some examples here. So for example, the motion of a point how should I say? Let's say marked. So let's see, the motion of a point marked on a blade of an electric fan, right? So that's a circular motion. For example, the hands of a clock, it's circular, right? It goes in a circle. So the hands of a clock. Right, so these are 2 examples, and I'm sure you can come up with many others. And now let's see the third one. Let's talk about periodic motion. So periodic motion. So in this case, let's say an object repeats its motion after some time. So repeats. Okay, let me write like this. Repeats its motion after some time. Okay. And now the examples that we have in mind are the following. So for example, the motion of a pendulum. Right, what else? The motion of a child in a swing on a swing. What else? The strings of a guitar. Okay, so we have plenty of options here. There's plenty of examples for these 3 So now let's talk about rectilinear motion. We would like to come up. So this is like let's look at it again. This is and also the picture. So this is a real world problem, rectilinear motion, and we want to interpret this. Let's do an abstraction of this, and let's come up with some mathematical meaning of rectilinear motion. So the first one, rectilinear motion. Okay, let's do this. And now we'll have three instances here. So we would like to talk about the position of an object on a line. Then we would like to talk about the velocity of that object. Then we talk about the acceleration of that object, and then we talk about the speed. So we have four things to talk about. So okay, let me put here something else. Okay, let me leave it like this. So the first thing, the position of the object, right? So the position on of the object on the line, because keep in mind that we have a rectilinear motion, and we said the object moves on a line. Let's just say s of t, right? The line is described by this function s of t, right? This is a function of t, right? Of time t. So let's call this is a function of time t. All right. The second one will be the velocity of the object. And this will be described by this function. Let's call this v of t. Right. So this is the function v of t. And here, the rate the rate of change. So the velocity will be described by the rate of change of f of s of t, right? With respect to the time t, with respect to time t, right? And this will be given by the formula v of t is nothing else than just the derivative, so ds over dt. So it's nothing else than just the derivative of the position with respect to t, right? So this is the, okay. Now let's see the third one. We would like to talk about the acceleration, and you will see that again this will be another derivative. So let's so the acceleration of the object. And we will call this a of t, right? Right. So this would be nothing else than the rate. So the rate of change of v of t with respect to time t. To time t, right? And now the last one, we would, the fourth one, we'll like to talk about the speed. So the speed, and here we will, okay. So here we will talk about the rate In fact, now let me put it like this, is the absolute value of velocity. All right, so this will have the following formula. So the speed is nothing else than just the absolute value of v of t. And again, this will be the absolute value of ds over dt, or if you want, the absolute value of s prime of t. Right, so that's the formula. Right, so this is what happens in the case of a rectilinear motion. And well, we will see what is the relation between these, but at this point, I think you can figure it out. I forgot to say about the acceleration. Oh my goodness. I jumped immediately. Well, okay, sorry about that. Because I was wondering, where is the formula for the acceleration? Well, as you can expect, the acceleration is nothing else than just the derivative of the velocity. So a of t, let's write it here, is nothing else than just dv over dt, or if you want, is the derivative v prime of t, or if you want, since the derivative is since v prime of t is the derivative of the position, this will be nothing else than just the second derivative of s with respect to t, or if you want, s second prime of t. And we have this formula. Okay, that's beautiful. This is what you need to know. The velocity is the derivative of the position. The acceleration is the derivative of the velocity, or is the second derivative of the position of the object, right? Keep in mind that the position of the object is a function of t, of time t. So that's what you need to know. And of course, the speed will be the absolute value of the derivative of s prime. So it's the speed will be the absolute value of the derivative of the velocity. All right, so I think we got this clear, hopefully. And now, rectilinear motion so here, let me just say, so an object that moves along a straight line, right, with position s of t, right, this position is a function s of t, has velocity v of t equal to the derivative of the position, so ds over dt, so this is s prime of t, right? And acceleration, and acceleration, and this acceleration will be nothing else than just this function a of t, which is the derivative of the velocity, so dv over dt, which is v prime of t, well, we said it, or is the second derivative of the position, or s second prime of t. Okay, we can say like that. And this is important when these derivatives exist. So these derivatives exist. So this is important. Okay, that's important. If the derivatives do not exist, then we're in trouble. And now, well, as you can see above, the speed of the object is the absolute value of the velocity. So let's write this. So the speed is the speed of the object is nothing else than the absolute value of v of t. Yeah, so putting everything together, this is what you need to know. And now let's point out some remarks. I want to point out some remarks before I go and do more applications, because I like to see some applications of these notions of the rectilinear motion. But before that, let's point out a remark, because I would like, I want you to know this. So remark, and this is the following. If so, the first thing is that if v of t, so it's the velocity, is positive, right? Keep in mind that the velocity is the derivative of the object. Then we can say that the object is advancing. Then the second one, if the v of t is less than 0, then we can say that the object is retreating. The object is retreating. Now, if the velocity v of t is 0, then the object is neither advancing nor retreating. Okay, so we say stationary. So that's how we call this, right? And now let's work with the acceleration. If a of t is positive, right, then the object is accelerating. And if the derivative, if the a of t is negative, then the object is decelerating. And now let's talk about units. I would like to mention something about units. And let me draw the following chart. So we have the distance. So the way we measure the distance, the way we measure the time, the velocity, and the acceleration. So we would like to measure these things here. So let's draw the following chart. Right? So let's say, so we measure the distance in meters, feet, for example, or miles. Or, you know, in Europe, we don't use miles. We actually use kilometers. I usually get confused when I say, if somebody tells me, well, how many miles is the kilometers? And I was like, oh my God. Anyway, the time will be measured. So if you want to measure in meters per second, so we'll have the velocity m over s, or the acceleration will be meters per second squared. So, or for example, this will feet will be for hours. So feet per hour is the velocity, and then you'll have the acceleration feet over h squared. And the same, let's do it like this. And guess what? The same thing will go for miles. So this will be hours and also kilometers. So this will be miles per hour. This will be kilometer per hour. You can measure like this if you want, or kilometer per hour h squared, and miles per h squared. Anyway, keep in mind that 3.28 feet is approximately like 1 meter. Also, 1.6 kilometers is it's approximately 1 mile, and also 1,609.33 meters is yeah, that's 1 mile. Anyway, it doesn't really matter. Let's put it like this. Okay, So this is what you need to know. All right, now let's see some examples. I'd like to dwell on some examples, and I think after this, probably I'm going to stop anyway, but let's see some examples. So example, let's call this exercise. God knows what number, I forgot the number, but anyway, let's call it exercise. So this is one of the exercises that I took from the textbook. So this says the following. So assume that that the position of an object moving along a line. So when we are told this, it's quite clear what kind of movement this is. It's given by the following function, right? S of t will be, let's take a cubical, so it's 3t cubed minus 40.5 t squared plus 162 t. Okay, this is one hell of a cubicle, right? And now for t, and actually I would like to restrict t from 0 to 8. And now we're asked the following. We want to find out the following. The first one, find the initial position. So find the initial position, velocity, right? And acceleration. Of the object, or actually for the object. Okay. The second one, discuss the motion. And then the third thing, compute the total distance traveled. Compute the total distance traveled. All right, so this is the problem. So let's see this. We'd like to address this. This is a very nice problem. In fact, we will see this could be like a very interesting midterm exam problem. Right, very interesting exam problem. And now let's see. So let's see the initial position. So we would like to see what happened at the initial position here. So what happened with the velocity? What happened to and the acceleration, right? At the initial position. What is the initial position? Well, it's basically when t equals 0. So that's the initial position. So in other words, we would like to, since I'm asked about velocity and acceleration, I'm basically asked to compute the derivative, right, of the motion of the object at 0, at the origin, right, because it's the initial, it's basically when it starts, and then the acceleration, which is the second derivative of or the first derivative of the velocity, if you want, right? So keep in mind that we're asked about velocity and acceleration. So these two things. All right, let's go for it. So we have this function. So initial position. So the initial position, right, is at t equals 0. So that's the initial position. So the object starts at the origin, so that's what you need to know. And the initial velocity is v of 0. So in other words, which is the derivative of s with respect to t when t equals 0. So it's s prime of 0. But the derivative, right, of t is nothing else than just, let's look at our function. So it's 3t squared, 3 cubed, sorry, minus 40 times 0.5 t squared plus 162 times t. So this would be equal to, if we compute the derivative, so this would be 9t squared minus 81t plus 162. So that's the derivative. And now when you evaluate this at 0 and ds over dt evaluated at t equals 0 will give us, when you put this, it'll be nothing else than just 162. All right, it's beautiful. So that's the initial velocity, right? So we compute the initial velocity, and now the initial acceleration right, is a of 0, which is nothing else than the derivative of the velocity. So it's dv over dt at t equals 0, which is nothing else than just 18t minus 81, right? That's the derivative evaluated t equals 0, and this would be nothing else than just 81. So that's it. So that's the story with the first part, with the initial position, velocity, and acceleration of the object. Now let's go with the second one. So let's talk about let's discuss the motion. I think this is where we would like to see what happens when the motion is positive, when the velocity is positive, when the acceleration is positive, when it's negative, and so on. So we'd like to see what happens to the object. Is accelerating, is decelerating, and the same for the object. We'd like to see if it's advancing or it's retreating. So for this, to discuss the motion, we shall identify the interval. So let's write this. So to discuss the motion, right? We shall identify, right, the time intervals with v of t positive, v of t equals 0, and v of t negative. So we need to identify this. Also, where a of t is positive and a of t is negative. So that's what we need to do. Oh my goodness! Now it will be there'll be a bunch of computations here. All right, let's see. So we know what? We know that v of t, what was v of t? Was 9t squared minus 81t plus 162. And now we can decompose this, so we can factor this, and this would be, so we can factor a 9 here. That's great, right? So we can factor 9. So it's t squared minus 9t plus 18, okay. Okay, okay, nice. So this would be t minus 3 times t minus 6. All right, beautiful. And now we have that v of t is 0, right? And this happens when t equals 3 or t equals 6, right? So basically, when t equals 6, t equals 3 or t equals 6, the object is stationary. Right? That's the word. When v of t is less than 0, this implies that 9 times t minus 3 times t minus 6, this is less than 0. And this will be equivalent with t minus 3 times t minus 6 is less than 0. So this will imply that, okay, so t will be between 3 and 6. So when this happens, when t is this open interval, 3 and 6. So when this happens, right? So this means that we can say that the object is is retreating. So in other words, the object is retreating on the interval 3, 6, you can say. And now let's see what happens when v of t is positive. So when when v of t is positive, then you will have something like 9 times t minus 3 times t minus 6 is greater than 0. So this means that t is less than 3 and t is greater than 6. So you can say that the object is advancing on the interval 0, 3 and 6, 8. Okay, on these two intervals. So this is what happens. But between 3 and 6, the object is retreating. So it goes advancing, then it retreats, and then it will advance again. Now let's see about the acceleration. So we have two things here. So let's see what happens when a of t is negative. So this would mean, oh my goodness, the acceleration. What was that? It was 18. So a of t was 18t minus 81. Okay, that's good. So this means that 18t minus 81 is negative. So this means that at some point 81, 9 over 2, so t is less than 9 over 2. So you can say that the velocity is decelerating. Ouch. So the velocity is decelerating, right? And now we have the other thing when a of t is positive. This means that 9t minus 2 is positive. So this means that t is greater than 9 over 2. So you can say that the velocity is accelerating on this interval, let's say 9 over 2 times 8. And let's say here, this is on the interval. What was it? 0, 9 over 2, open interval. Okay. So this is what happens. And now, so this is the, but now we can, what else do we need to do? We want to compute the total distance traveled. And now let's draw a picture. In fact, let's see what happens. So let me draw the following chart. So we want to see on some intervals how much distance this object traveled. So let's see, we have time, we have position, and we have velocity. So let's look at these three. And now let's see. When t equals 0, so we'll have the position will be 0, and the velocity was 162, right? We have computed this. When t is less than 3, we don't have anything here, and v of t was positive, so it was advancing the object. So that's what we said, right? If we look above, yeah, that's what we said. Okay. What else? When t equals 0, maybe I should say, wait. So when t equals 3, sorry, right? Okay, so yeah, this is what happens when t equals 3. We have the position with s of 3, right? S of 3 is 202.5, and v of 3 is 0, right? Now let's see what happens. So the object is not advancing or retreating. It's and now let's see what happens when t is in the interval 3, 6. Well, we have nothing, and with the position, but the derivative v of t is negative, so the object is retreating. And now, when t equals 6, we have that what? We have that s of 6 is 162, and v of 6 is positive. Oh, sorry, v of 6 is 0. Okay, so v of 6 is 0. And now when t is between 6 and 8, so we have two more cases. So and t equals 8, and that's it. All right, let's see. What happens here when t is between 6 and 8? Nothing happens here, but we know that v of t will be positive. So basically, the object is advancing. That would be a very nice picture when we draw it. And when t equals 8, s of 8 is 240, and v of 8 is 90. All right, finally, let's draw the picture. All right, let's see. So let's draw the like this. So it starts from the axis. So this is the moment when t equals 0. So it starts from here. So our object will go, in fact, let me, no, I need to. So it will go like this, straight, right? So this would be when t equals 6, for example, the velocity will be 0, and s is 162. Then it will go at t equals 3 here, the moment the velocity is again 0, and s is 202.5. And now it will go like this, right? So this is what, and now it goes like this, and like this. Okay, maybe I should put this like, because this is rectilinear motion, but that doesn't look like a line. Maybe I should make it look like, right? Anyway, so we have this. So we'll go like this. And here I'll have a point. And now here we'll have, so this will be, let's see, so here is t equals 3. Here I'll have t equals 6. Again, v will be, wait, what am I doing? Okay, I wrote it here. Sorry about that. So t equals 6. V will be 0. And the S is 162. And here at t equals 0, I'll have V is 162 and S is 0. Now it keeps going at T3, T6. And now at the time when t equals 8, I'll have V equals 90 and S will be 240. And now guess what? Well, the distance from 0 to 3 is 202.5. Look at it here. The distance from 3 to 6 is 202 minus 162, right? Let's write this. So let's look at these guys. So the distance from 0 to 3 is 202.5. Then the distance from 3 to 6 when in this interval is 202.5 minus 162, which will give us 40.5. And the distance, right, from when t is between 6 and 8, this will be nothing else than just 240 minus 162, which is nothing else than just 78. And now if we want to see the total distance traveled, so we just have to add these three guys. So the total distance traveled is 202.5 plus 40.5 plus 78. And if you add these three, so it will be 321. And that's it. That's the final answer. So this is how you solve this problem. Anyway, well, you know, I think I'm going to stop here. I don't want to go too much over time. I think it's a good place to stop. Well, I would like you to look in my notes. Well, I didn't discuss. There's another physics problem, which the motion there is somewhat circular. So you have a projectile, and you want to you launch that projectile. So you project that thing. That object, so you can fire it, you can throw it, whatever, vertically, and you would like to see at what height that object is projected. So basically, you want to see the formula for the height of the projectile. You would like to see what happens to the initial velocity, the initial height, acceleration due to gravity, and so on. Anyway. You will look that was the second example, but I would like to not do it. I think we had enough. And I think this is a good place for me to stop. Thank you very much.